A question at the edge of physics. For as long as we've looked into the night sky, we've wondered, is the universe navigable beyond the speed of light? Could there be hidden passageways between distant stars, or even shortcuts across galaxies? The concept of a wormhole sits at the intersection of hard physics and breathtaking imagination. On one hand, it is a mathematical possibility hidden within Einstein's theory of general relativity. On the other, it is a staple of science fiction, an elegant solution to the problem of distance in a vast, seemingly untraversable cosmos. But what are wormholes really? Are they plausible structures of space-time waiting to be discovered or created? Or are they illusions, mathematical artifacts of equations that cannot exist in reality? This documentary explores the history, science, and mysteries of wormholes. From their birth in Einstein's equations to the bold frontiers of modern physics, we'll unravel what these hypothetical tunnels mean for space, time, and perhaps even the future of humanity. The fabric of space-time. When Albert Einstein first published his theory of general relativity in 1915, he didn't know that he was creating wormholes. That's because back then, no one was thinking about wormholes. In fact, they wouldn't enter the popular imagination for another 40 years. What Einstein was doing was creating a new way to understand gravity, an effect we all experience every day, but have never really been able to explain. His idea was that gravity wasn't a force that objects exert on each other, as Isaac Newton had suggested, but rather a curvature in the fabric of space-time caused by those objects. Imagine the surface of a trampoline. If you place a bowling ball in the center, it will cause the surface to sag. If you then roll a marble across the trampoline, it will not continue in a straight line, but will curve toward the bowling ball before continuing on its way. This curving of space around massive objects is what causes planets to orbit stars, moons to orbit planets, and even light to bend around stars. But here's where things get weird. According to Einstein's equations, this warping of spacetime can be reversed. So that means if you were to take 2 points in spacetime very far apart, you could keep curving them together until they intersect. The result would be a tunnel-like structure connecting the 2 points. And because time is part of spacetime, that tunnel would also connect the 2 points in time. It's like folding a piece of paper so that 2 distant points touch. This is the basic idea behind a wormhole. However, this does not necessarily mean that wormholes actually exist. After all, Einstein's equations are just a set of mathematical relationships. They don't tell us anything about the nature of reality. It's like if you have a friend named Joe, and you know that Joe is 6 feet tall based on some measurements you've taken. You might use Joe's height to predict how far a ball will bounce when it hits Joe in the chest. But just because you have an equation for ball bouncing and human height doesn't mean that balls actually bounce off people. Similarly, the fact that wormholes are a mathematical possibility hidden within Einstein's equations does not mean that they actually exist. It's only when we gather evidence from the real world that we can begin to separate possibilities from reality, wormholes, and the Big Bang. To further complicate matters, the mathematics that describes wormholes breaks down at the Big Bang. This is a major obstacle for anyone trying to study them. That's because our best theories about the early universe, such as inflationary theory, require that space-time be flat. In other words, a wormhole cannot exist in a flat universe. So either the universe began with wormholes, which seems unlikely, or it did not. In that case, wormholes could not have played any role in the Big Bang. Despite these challenges, scientists continue to study wormholes because they may hold the key to some of the biggest mysteries in physics, such as the nature of dark matter and dark energy. One leading hypothesis for dark matter, for example, is that it consists of particles that can only travel through wormholes. This would explain why we never see these particles directly, since they would be hiding inside wormholes. By studying wormholes, then we may be able to shed light on some of the most elusive phenomena in the cosmos. What do you think? Wormholes are one of the most fascinating topics in physics, and we want to hear your thoughts. Do you think wormholes actually exist? And if so, do you think they could be used for interstellar travel? The most famous wormhole in the world may also be its least scientific. At least that's one opinion about the cosmic dreadnought depicted in the original Star Trek series. Its gaping maw serves as a portal for intrepid explorers journeying to new worlds. But the modern idea of a wormhole goes back much farther, to a time when space travel was still a distant dream. Our story today is one of many chapters in the history of the cosmos. And here we return to the legendary wormhole once again. This time we will take a journey from the birth of modern astronomy to the latest news and discoveries in the universe. Let's get started. Wormholes have been staples of science fiction for decades, often used to shrink vast distances and make intergalactic travel a little more plausible. But did you know the first wormhole appeared over 40 years before humans ever set foot on the moon? It turns out that the earliest known depiction of a wormhole can be found on the ancient Greek island of Delos in the form of a relief carving dating back to around 700 BCE. However, it wasn't until the 1930s that the concept of wormholes began to appear in more modern literature. In his 1937 novel, A Logic Named Joe, American author Edward Bellamy featured a device called a transmographere, which allowed characters to travel instantaneously between different parts of the solar system. Though never described as a wormhole, this fictional technology seems to align with our modern understanding of how wormholes work. Over a decade later, in 1947, a British writer named Murray Leinster published a short story titled The Stargate, which introduced readers to an artificial gateway between Earth and a distant planet called Alpha Centauri. This narrative marked a significant shift in how wormholes were being portrayed, moving away from purely fantastical devices and toward something that resembled modern concepts of wormholes as physical phenomena. However, it was in the 1960s that the term wormhole really caught on thanks to a pair of influential science fiction authors. In his 1963 novel, The Making of the Moon, American writer Robert A. Heinlein used the word wormhole to refer to a type of interstellar gateway. Meanwhile, British author Brian Aldiss popularized the term even further with his 1965 novel The Malaysia Hawks, which featured a wormhole as a key plot device. As science fiction continued to explore the possibilities of wormholes, so did astronomers and physicists. And in the coming years, these two realms would collide in unexpected ways. For centuries, astronomers had relied on Newtonian physics to understand the motion of celestial bodies. However, in the early 20th century, Albert Einstein's theory of general relativity forced a radical rethinking of gravity and the nature of the universe. According to general relativity, massive objects warp the fabric of spacetime around them, causing other objects to move along curved paths. Although initially controversial, Einstein's ideas soon found support from astronomers who realized that Newtonian physics failed to explain certain observed phenomena, such as the bending of starlight around the sun. Meanwhile, physicists were hard at work unraveling the mysteries of quantum mechanics, a new theory that governed the behavior of matter at the atomic and subatomic levels. Quantum mechanics introduced concepts that seemed almost alien to classical physics, such as wave-particle duality and the uncertainty principle. Despite these developments, the marriage between general relativity and quantum mechanics remained elusive. Physicists struggled to reconcile the deterministic, predictable nature of general relativity with the probabilistic, unpredictable nature of quantum mechanics. The problem lay in the fact that general relativity treated spacetime as a smooth, continuous entity, while quantum mechanics suggested that spacetime should exhibit some granular properties. It was against this backdrop that the concept of a wormhole emerged as a potential solution to one of physics's most perplexing riddles. To truly comprehend wormholes, one must first grasp the concept of an event horizon. An event horizon is the boundary of a region in spacetime from which nothing, not even light, can escape. Imagine crossing the threshold into a one-way street. Once inside, there's only one direction you can go: forward. Looking back won't help, since you're barred from turning around. No matter how fast you move, you can't alter the outcome. You've entered a region of no return. In essence, that's what an event horizon represents, a point of no return in space-time. When anything, whether light or matter, crosses this boundary, it's trapped forever within the confines of a black hole. Event horizons play a pivotal role in shaping our understanding of the universe. They are the defining feature of black holes, regions of space from which nothing can escape once it crosses the threshold. The boundary of this region is known as the event horizon. Anything that ventures across this horizon, including light, is inexorably drawn towards the center of the black hole and cannot escape to communicate with the outside universe. In the late 1930s, physicists were exploring the implications of Einstein's theories when they stumbled upon something remarkable. They discovered that under certain circumstances, The event horizon of a black hole could be extended infinitely, effectively creating a tunnel-like structure through spacetime. This groundbreaking realization marked the birth of the Einstein-Rosen bridge, later popularized as the wormhole. The concept was simple, yet profound. If two black holes were brought close enough together, their event horizons could merge, forming a bridge-like connection between them. Any object or information entering one end of the wormhole would emerge at the other end instantaneously, regardless of the vast distances involved. This discovery sent shockwaves through the scientific community, opening up new avenues of research and speculation. Some physicists began to wonder if such wormholes existed naturally in the universe, potentially providing shortcuts for interstellar travel. Others delved deeper into the mathematics, trying to understand the properties and characteristics of these theoretical wormholes. The implications were staggering. If confirmed, the existence of wormholes would revolutionize our understanding of the cosmos and our place within it. It would mean that the universe was far more interconnected and accessible than previously thought. However, despite the excitement surrounding this discovery, scientists were quick to point out the challenges associated with harnessing wormholes for practical applications. They knew that to explore the interiors of black holes or traverse these theoretical wormholes, new technologies and scientific breakthroughs were needed. Nevertheless, the discovery of the Einstein-Rosen bridge ignited the imagination of scientists and the public alike. The possibility of traversing the vast distances of space with relative ease captured the collective consciousness and inspired countless works of science fiction. The allure of the unknown and the promise of new discoveries fueled a sense of wonder and excitement about the potential for human exploration and discovery. The discovery of the Einstein-Rosen bridge served as a catalyst for pushing the boundaries of scientific inquiry and exploration. It sparked a renewed interest in the mysteries of the cosmos and inspired generations of scientists to reach for the stars. However, the concept of wormholes soon gave way to a more familiar image in the 1960s and 70s. Largely due to the influence of science fiction, authors like Robert Heinlein and Brian Aldiss helped popularize the term wormhole in their novels, shaping our cultural understanding of these mysterious phenomena. As wormholes entered the realm of science fiction, they quickly captured the public's imagination. Science fiction writers began incorporating wormholes into their stories, depicting them as portals to distant worlds or alternate dimensions. These imaginative tales transported readers to uncharted territories of the cosmos, leaving us with a legacy of wonder and possibility. Despite their enduring popularity in science fiction, the scientific understanding of wormholes remained elusive. For decades, wormholes remained largely theoretical constructs, existing primarily on paper as solutions to Einstein's equations. Scientists grappled with reconciling wormholes with quantum mechanics and understanding their formation and stability. But it was until the late 20th and early 21st centuries that researchers began to unravel some of these mysteries. Advances in physics led to a deeper understanding of wormholes, shedding light on their properties and behavior. Scientists explored the possibility of using wormholes for time travel, opening up new frontiers in theoretical physics. The quest to understand wormholes continues to captivate scientists and researchers today. With each new discovery, we inch closer to unraveling the secrets of these enigmatic cosmic structures and their potential impact on our understanding of the universe. Wormholes have transcended their origins in theoretical physics to become cultural icons. They have inspired countless works of art, literature, film, and television, leaving an indelible mark on our collective imagination. From the pages of sci-fi novels to the silver screen, wormholes continue to captivate audiences and remind us of the endless wonders that lie in wait. One prominent depiction of a wormhole comes from the renowned science communicator Carl Sagan, who famously portrayed it as a cosmic on-ramp in his 1994 book, Cosmos. This metaphor has resonated with many viewers and readers, helping to popularize the concept of wormholes among the general public. Similarly, the visual representation of a wormhole as a tunnel-like structure, connecting two distant points in space has become widely accepted. This image has been reinforced by numerous science fiction films and television shows, cementing the wormhole's status as a cultural icon. The impact of these depictions on our understanding of wormholes is undeniable. By visualizing wormholes as cosmic on-ramps or tunnels, We've created a shared mental model that helps us grasp their immense scale and potential implications. These representations have fueled our fascination with wormholes and inspired countless individuals to learn more about these enigmatic phenomena. As we continue to explore the vastness of space and the complexities of the universe, the allure of wormholes will undoubtedly endure. Their ability to connect distant realms of the cosmos captures our innate desire for exploration and discovery. So next time you find yourself gazing up at the night sky, remember that within those twinkling stars may lie hidden wonders that defy our current understanding. And who knows, with future scientific advancements, we may one day uncover the secrets of wormholes and unlock the full potential of these extraordinary cosmic gateways. Iconic objects. Traversable wormholes. In the realm of theoretical physics, few concepts capture the imagination quite like wormholes. These hypothetical tunnels through space-time have become staples of science fiction, promising faster-than-light travel and journeys to distant worlds or even alternate universes. But wormholes aren't just figments of science fiction. They arise naturally from equations that describe our universe. In fact, one of the most famous solutions to Einstein's equations was the wormhole itself. Given the right conditions, wormholes might actually exist. But Einstein and Rosen gave us the first glimpse of wormholes. Their bridges collapsed too quickly to be used. If wormholes were to move from mathematical quirks to serious physical candidates, physicists had to imagine versions that could stay open traversable wormholes. So here's our list of the top 3 iconic wormhole objects that you should know about. No. 3. The Morris-Thorne wormhole. In 1988, physicists Kip Thorne and Michael Morris formalized the first widely discussed model of a traversable wormhole. Thorne was motivated in part by a phone call from science fiction writer Carl Sagan, who was working on the novel Contact. Sagan wanted his story grounded in real physics, so he asked Thorne, could a character realistically travel across the galaxy through a wormhole? Thorne and Morris produced a landmark paper that answered, yes, if certain conditions could be met. Their model described a wormhole with 2 mouths located at distant points in spacetime, a throat that connects them. Stability maintained by an unusual ingredient, exotic matter, which has negative energy density. This negative energy would act as a kind of anti-gravity, holding the wormhole open against collapse. In principle, such a wormhole could be traversed by a spaceship, allowing instantaneous travel between stars, or even between different universes. The Morris-Thorne wormhole became an icon, not just in science fiction, but also in serious theoretical research, to black hole pairings. Another avenue of wormhole speculation comes from black holes themselves. Could 2 black holes, under certain conditions, form a connected tunnel through spacetime? One idea is the Einstein-Rosen bridge interpretation of black holes, that a black hole and its mathematical mirror, a white hole, could be connected. The black hole swallows matter, the white hole expels it, and together they form a wormhole. But in reality, white holes are entirely hypothetical. No evidence for their existence has ever been found. Still, black holes remain central to wormhole models, because their extreme warping of spacetime mimics the conditions required for a tunnel to form. For instance, black hole mergers are thought to produce ripples in spacetime called gravitational waves. Some physicists speculate that these waves could carry information across the event horizon, potentially linking to black holes together. It's a radical idea, and one that would revolutionize our understanding of black holes. But the notion that black holes can form wormholes highlights the creative ways physicists think about connecting space and time. Number 1. The thin shell wormhole. Another iconic concept is the thin shell wormhole. It's constructed by cutting and pasting different spacetimes together. Imagine slicing 2 regions of spacetime and then sewing them together at a shared boundary. The mathematics allows such structures, though. Again, exotic matter would be required to stabilize them. This method is elegant because it doesn't depend on black holes directly. Instead, it uses relativity's flexibility to craft wormhole-like geometries. The idea of a thin shell wormhole captures the imagination because it sidesteps some of the immediate paradoxes of wormholes. By taking slices of existing spacetime and joining them, it avoids the need for exotic matter, at least in the classical limit. However, this approach does not come without its own set of challenges. The question of how to join 2 regions of spacetime without introducing new problems remains an active area of research. Additionally, the use of exotic matter in stabilizing wormholes continues to be a sticking point. Despite these challenges, the thin-shell wormhole remains an iconic concept in theoretical physics. Its elegant mathematical structure and potential to provide a new perspective on wormholes make it a compelling subject of study. Further research into this concept may help to unlock new insights into the nature of wormholes and their role in our universe. But there's another type of wormhole that doesn't rely on exotic matter or black holes, and it arises naturally in our theories of gravity. Gravitational wormholes emerge from the mathematics of general relativity in situations where matter is distributed in a particular way. They don't require any adjustments to the laws of physics. But they do raise their own set of intriguing questions. Gravitational wormholes challenge our understanding of gravity and the nature of spacetime. By exploring these natural solutions to Einstein's equations, physicists hope to gain a deeper understanding of the fundamental laws that govern our universe. Wormholes are a staple of science fiction, often depicted as gateways to distant worlds or alternate dimensions. But the concept of wormholes goes beyond the realm of fantasy. It's a fascinating area of theoretical physics that has captured the imaginations of scientists and science enthusiasts alike. So here's everything you need to know about wormholes. What is a wormhole? A wormhole is a hypothetical region of spacetime that allows for travel between two distant points by taking a shortcut through a tunnel-like structure. This structure resembles a worm, and hence the name wormhole. The concept of wormholes was first proposed by physicists Albert Einstein and Nathan Rosen in 1935. They are solutions to Einstein's equations of general relativity, which describe the behavior of gravity. How do wormholes work? According to Einstein's theory of general relativity, space and time intertwined in a four-dimensional fabric called spacetime can be warped and distorted by mass and energy. This means that two distant points in spacetime may be brought together by a wormhole. When two distant points are connected by a wormhole, the distance between them effectively becomes zero. This means that an object traveling through a wormhole would arrive at its destination instantaneously, regardless of how vast the distance may seem. What are the different types of wormholes? There are several types of wormholes, including intergalactic wormholes. These connect to points in space, allowing for travel between two different galaxies. Q-dimensional wormholes. These connect to points in different dimensions, allowing for travel between parallel universes or alternate dimensions. Intragalactic wormholes. These connect two points within the same galaxy, allowing for faster-than-light communication or travel. Are wormholes possible? The existence of wormholes is still purely hypothetical, and there is no evidence that they exist in our universe. However, they are mathematically possible solutions to Einstein's equations of general relativity. Some physicists believe that wormholes may exist, while others remain skeptical. What are the challenges of detecting wormholes? The detection of wormholes presents numerous challenges. They are extremely difficult to detect due to their hypothetical small size and the immense energy required to create or maintain them. Even if wormholes do exist, they may be extremely rare, making their detection all the more challenging. What is the significance of wormholes? Wormholes are significant in theoretical physics because they raise fundamental questions about the nature of space-time and the laws that govern our universe. They challenge our understanding of gravity and the concept of infinity. Wormholes also have implications for cosmology and astrophysics, particularly in relation to the Big Bang theory and the heat death of the universe. What is the future of wormhole research? Research into wormholes is ongoing, although progress is slow due to the lack of observational evidence and the immense challenges involved in testing hypothetical ideas. Many physicists remain intrigued by the concept of wormholes and continue to explore their properties and potential implications for our understanding of the universe. Conclusion: wormholes have captivated the human imagination for decades, promising a way to travel to distant worlds and alternate dimensions. While these fantastical ideas may seem out of reach, the concept of wormholes has practical applications in fields such as quantum computing and cryptography. As technology advances, we may find new ways to harness the power of wormholes to solve real-world problems. Who knows? Maybe one day we will discover that wormholes are not just a figment of our imagination, but a key to unlocking the mysteries of the universe. Wormholes demand extraordinary physics, negative energies, exotic geometries, causality violations. But if we could pull it off, what could we use them for? How would we engineer a wormhole? What would it mean for humanity? Turning science fiction into engineering challenges, the notion of traversing wormholes has long captured the imagination of science fiction writers. Over a century after their mathematical discovery, engineers are beginning to ask whether wormholes could ever be built. But first, we need to get past the idea that wormholes exist only in science fiction. First, we have to assume that wormholes exist. Second, we have to understand the physical principles governing them. Third, we have to devise a method of creating and stabilizing wormholes. Finally, we have to figure out how to traverse them. The good news is that scientists have made remarkable progress in answering the first question. The bad news is that much of this progress leaves scientists no closer to a consensus. Wormholes, according to Einstein's general theory of relativity, are as real as anything else in the universe. They're solutions to Einstein's equations, which means they fit the mathematics of relativity. The trouble begins when we try to ask what those solutions mean in the real world. Is a wormhole an actual tunnel through space, a doorway into another universe, shortcut through time? There are many possibilities, but none are well understood. Making sense of the wormhole mathematics before we can design a wormhole, we need to make sense of the mathematics. Einstein's equations tell us that a wormhole is a solution, but that doesn't mean we know how to build one. A wormhole can be described by a single number, d, the size of its throat, or equivalently, the size of its mouth. Mathematically, there's nothing special about a wormhole's throat, so let's focus on it. Here's what we know. The inside of the throat must be empty because anything inside the throat would block the path between the mouths. The second law of thermodynamics tells us that entropy wins every time. The throat will tend to expand until all available states of the mouth are accessible. If the mouths aren't trapped, they can move around freely and the wormhole can shrink. The smaller the wormhole, the greater the pressure difference between its ends. As the wormhole shrinks, the pressure difference grows, and the mouths move further apart. Eventually, the mouths reach the Planck scale, and the wormhole can't shrink any further. This is called a black hole, and it happens when the total mass of the wormhole exceeds 2/3 times the mass of the original mouths. A wormhole can be created when two massive objects get close enough to each other. As they approach each other, the wormhole grows and becomes wider. At some point, however, the gravitational repulsion of the two masses prevents them from getting any closer, and the wormhole stops growing. If the two masses are equal, then the wormhole reaches a stable size, and the larger the masses, the larger the wormhole. If the masses are unequal, then the heavier mass pulls the lighter mass toward it, and the wormhole continues to grow until the two masses meet. When this happens, the wormhole becomes a black hole, and all of the mass of the system falls into it. Trapping the mouths once a wormhole has been created, the next problem is to trap its mouths so it doesn't collapse. One way to do this is to put the mouths into orbit around a heavy object, like a star. However, as the mouths move around, they will inevitably come close enough to each other to collapse. The only way to avoid this is to keep the mouths very far apart, which requires a lot of energy. Another option is to anchor the mouths to fixed locations. For example, one mouth could be attached to a planet while the other mouth could be anchored to a black hole. However, anchoring a mouth to a planet is tricky because the mouth is extremely heavy. Planets can't hold things that way more than they do. We haven't yet figured out how to solve this problem. Wormhole collisions. One way to think about what happens if two wormholes collide is to imagine the mouths as being made of ordinary matter. If the mouths were made of ordinary matter, then the wormholes would simply collide like billiard balls. However, the mouths of wormholes are not made of ordinary matter. They're made of exotic matter. Exotic matter has negative energy density and negative pressure. If the mouths of wormholes were made of exotic matter, then the wormholes would repel each other. But how do they repel each other? Well, it turns out that the repulsion force between two wormholes is exactly the same as the gravitational attraction force between two black holes. The reason for this is that the energy density of a wormhole is proportional to its mass. Therefore, the pressure of a wormhole is proportional to its surface gravity. The surface gravity of a black hole is proportional to its mass. Therefore, the pressure of a black hole is proportional to its mass. Since the mass of a wormhole is proportional to its energy density, the gravitational attraction force between two black holes is proportional to the product of their masses. The repulsion force between two wormholes is proportional to the product of their pressures, which is the same thing. Thus, the repulsion force between two wormholes is exactly the same as the gravitational attraction force between two black holes. What this means is that if two wormholes get too close to each other, they will merge to form a single wormhole. The new wormhole will have a mass equal to the sum of the masses of the original wormholes, and it will be twice as wide as either of the original wormholes. Wormhole surgery, one of the most fascinating aspects of wormholes, is the possibility of using them to travel through time. This is known as wormhole surgery. The basic idea is to use a wormhole to travel backwards in time to kill one's father. This would prevent one's own birth, thus eliminating the need for a wormhole. Sounds crazy, right? No, it's actually not as crazy as it sounds. It turns out that wormhole surgery is logically possible. This was first pointed out by Ronald Mallet in 1967. Mallet showed that if you have a wormhole connecting to points in spacetime, then you can use that wormhole to travel backwards in time to arrive at a point in the past. However, there's a catch. The point you arrive at must be causally disconnected from the point you depart from. In other words, you can't go back and change anything. You can only go back and observe things. This is why wormhole surgery is sometimes called closed time-like curve therapy. Using wormholes for energy transport, another interesting application of wormholes is for energy transport. Suppose you have a wormhole connecting to points in spacetime. Then you can send energy from one point to the other without violating the speed of light limit. This is because the wormhole provides a shortcut through spacetime. Energy can travel faster than the speed of light along a curved path, as long as it doesn't travel faster than the speed of light in a straight line. This means that you can use a wormhole to send signals faster than the speed of light, but you can't use it to send messages faster than the speed of light. Wormholes and the fate of the universe. Some people believe that wormholes will play an important role in the fate of the universe. They argue that as the universe expands, matter will eventually be pulled apart, and the only thing that will remain will be wormholes. This is because wormholes are the only thing that can survive the expansion of the universe. Everything else will eventually be ripped apart. The theory goes that the universe will consist of an infinite number of wormholes, each containing a black hole at one end. These wormholes will be the building blocks of the universe. They will allow matter to clump together again, and eventually stars and galaxies will form once again. This process will repeat itself over and over again, and the universe will eventually heat death. So we still have a lot to learn about wormholes, but one thing is for sure. They are one of the most exciting developments in modern physics. Maybe someday we will discover that they are real, and maybe someday we will even be able to travel through them. In the vast expanse of space and time, the concept of wormholes has captured the imagination of scientists and science enthusiasts alike. These theoretical tunnels that connect distant points in the cosmos have long been relegated to the realm of science fiction. But recent scientific breakthroughs have brought the possibility of wormholes closer to reality than ever before. The idea of traveling through a wormhole can seem like a distant mathematical abstraction. After all, wormholes are solutions to Einstein's equations of general relativity, a theory that describes the behavior of gravity. However, the implications of these equations extend far beyond the confines of academia. They challenge our understanding of the physical laws that govern the universe and raise profound questions about the nature of reality itself. As we continue to probe deeper into the mysteries of the cosmos, the line between science fiction and scientific possibility becomes increasingly blurred. In this exploration, we will delve into the cutting-edge research that is shedding new light on wormholes, revealing their potential as gateways to new realms of discovery. Join us as we uncover the secrets of these enigmatic structures and discover how they may revolutionize our understanding of the universe. One promising approach lies in the realm of quantum mechanics. By harnessing the bizarre properties of subatomic particles, researchers have made significant strides in creating conditions that mimic the extreme energies required to keep a wormhole open. Experiments involving entangled photons have shown that it is possible to manipulate quantum states in ways that could potentially be used to stabilize a wormhole. These experiments not only demonstrate the feasibility of creating wormholes, but also provide insights into the nature of quantum entanglement and its role in shaping the fabric of reality. However, the quest to understand wormholes does not end with quantum mechanics. Researchers are also exploring the potential use of artificial intelligence and machine learning algorithms to simulate the behavior of wormholes. By analyzing vast amounts of data and identifying patterns, AI-powered simulations can provide valuable insights into the complex dynamics of wormhole physics. This approach has led to the development of innovative techniques for detecting and characterizing wormholes, opening up new possibilities for exploration. But the significance of wormholes extends beyond their potential as scientific tools. They also offer a unique window into the mysteries of black holes. By studying the behavior of particles near a wormhole, researchers can gain a deeper understanding of the extreme conditions found near black holes. This knowledge can shed light on some of the most perplexing phenomena in the universe, such as the event horizon and the singularity. Despite the progress that has been made, there are still many challenges that lie ahead. One of the major obstacles is the need for extremely high levels of energy to create and maintain a wormhole. This energy requirement far exceeds the capabilities of current technology, making it difficult to conduct large-scale experiments. Additionally, the stability of wormholes is another area of concern. They tend to collapse quickly, making it challenging to study their properties or send objects through them. However, researchers are working tirelessly to overcome these obstacles and develop new technologies that can push the boundaries of our understanding. One promising avenue of research involves the use of nanotechnology. By manipulating matter at the atomic level, scientists may be able to create stable structures that can support wormholes. Another area of exploration is the use of superconducting materials, which can conduct electric current without any energy loss. These materials could help researchers create the strong magnetic fields required to stabilize wormholes. Moreover, advancements in computing power are also playing a crucial role in simulating wormhole behavior and identifying optimal conditions for their creation. But the quest to understand wormholes is not just about pushing the boundaries of scientific knowledge. It also has the potential to revolutionize our everyday lives. One of the most exciting applications of wormhole research is the possibility of developing new forms of communication. By sending information through a wormhole, messages could be transmitted instantly over vast distances, bridging the gaps between civilizations and potentially leading to unprecedented levels of global connectivity. Furthermore, wormhole research has implications for the future of space travel. By harnessing the power of wormholes, spacecraft could travel much faster than the speed of light, opening up new possibilities for exploring the universe. This could lead to the discovery of new worlds and resources that could benefit humanity for generations to come. As we continue to unlock the secrets of wormholes, the ethical considerations surrounding their use become increasingly important. The ability to travel through wormholes raises profound questions about the nature of time and the possibility of time travel. It is crucial that we explore these ethical dilemmas and ensure that the use of wormholes aligns with our values and safeguards the integrity of our universe. But despite the challenges and ethical considerations, the potential benefits of wormhole research are simply too great to ignore. As we continue to push the boundaries of scientific exploration, we must embrace the unknown and be willing to venture into the uncharted territories of physics. Who knows what wonders and discoveries await us on the other side of the wormhole? So let us continue to invest in research, support scientists, and dream big about the possibilities that lie ahead. Who knows? We may just find that the universe has even more surprises in store for us. And if you're ready to take your own journey through the cosmos, then be sure to follow for more updates on our latest videos. Together we can explore the wonders of the universe and discover what lies beyond the wormhole. We've discussed the immense energy requirements. Now let's shift to the equally critical issue of controlling such forces. De Sitter explained that maintaining a wormhole's structural integrity demands a delicate balance of forces. The exotic matter holding the wormhole together must be precisely regulated. The tiniest imbalance can lead to the collapse of the wormhole. To illustrate the complexity of this process, consider the following analogy. Imagine a tightrope walker carefully balancing on a high wire strung between two buildings. The tightrope walker must constantly make minute adjustments to their position and movements to counteract external disturbances and maintain their balance. Similarly, stabilizing a wormhole requires precise control over the distribution and movement of exotic matter to counterbalance the forces that threaten to tear it apart. Moreover, the control systems needed to regulate the exotic matter must be incredibly responsive. Any delay or inaccuracy in the control signals could have catastrophic consequences, causing the wormhole to collapse suddenly. This demands advanced technology and real-time monitoring capabilities far beyond our current technological reach. An additional layer of complexity arises from the fact that the internal environment of a wormhole is highly hostile and dangerous. The intense gravitational forces, extreme temperatures, and radiation levels make it extremely challenging to deploy and maintain the control infrastructure necessary to stabilize the wormhole. This harsh environment poses significant obstacles to the design and functionality of the control systems, requiring innovative solutions to ensure their survival and effectiveness. Furthermore, the control of a wormhole involves intricate feedback mechanisms to monitor and adjust the behavior of the exotic matter. Sophisticated sensors and data analysis systems are needed to collect real-time information about the state of the wormhole and translate it into control commands. These feedback loops must operate with minimal latency to respond effectively to any changes or disturbances that threaten the stability of the wormhole. To achieve this level of control, we would need to develop advanced technologies for detecting, manipulating, and stabilizing exotic matter. We would also need to create robust control systems capable of operating in extreme environments and responding in real time to maintain the integrity of the wormhole. While the prospect of controlling a wormhole may seem daunting, it is not entirely out of reach. With continued research and technological advancements, we may one day be able to develop the necessary tools and techniques to tame these powerful cosmic entities. However, it is important to note that the successful control of a wormhole would represent an extraordinary achievement in engineering and science. It would push the boundaries of our current understanding and capabilities and require international collaboration and investment to realize. Despite the challenges, the potential benefits of controlling wormholes are immense. They could revolutionize space travel, communication, and our understanding of the universe. Therefore, investing in research and development in this field is not only ambitious, but also holds the promise of transforming our world in ways we can only begin to imagine. Are wormholes nothing but fantasy, a mere figment of science fiction writers' imaginations? Or do they hold a place in the real world of physics? What does it mean for an object or event to be real? These are the kinds of questions we'll explore today as we look at wormholes, those theoretical tunnels through space-time that have captured the popular imagination. Today we'll consider what wormholes are, why Einstein didn't like them, and why modern physicists think he was wrong. We'll also touch on the fascinating history of wormholes in thought experiments, sci-fi movies, and everything in between. So, buckle up for a journey through the science of science fiction. The idea of wormholes grew naturally from Einstein's theory of general relativity. In 1916, Ludwig Flamm first noticed that Einstein's equations described not just black holes, but also mirror solutions, tunnels connecting distant points in spacetime. By 1935, Einstein and Nathan Rosen formalized this idea in what became known as the Einstein-Rosen bridge. Though unstable and untraversable, it showed that relativity permitted spacetime tunnels. Later, physicists took the concept further. John Wheeler, in the 1950s, coined the term wormhole and introduced the idea of spacetime foam, a frothing microstructure of spacetime at the quantum scale where tiny wormholes might pop in and out of existence. By the late 1980s, Kip Thorne and his collaborators went further, showing that if exotic matter existed, wormholes could, in principle, be traversable. Thorne even pursued this partly to provide a scientifically grounded explanation for time travel in fiction, a request made by Carl Sagan while writing Contact. In addition to their appearance in fiction, wormholes have also played a significant role in theoretical physics.
Oh, yes.
They serve as valuable tools in thought experiments. For example, wormholes can be used to test the limits of causality and time travel. If one mouth of a wormhole is accelerated close to the speed of light, time dilation makes it younger than the other mouth. In principle, this creates a time machine raising paradoxes like the grandfather paradox. This forces physicists to confront whether the laws of physics allow or prohibit time loops. Wormholes also test our understanding of exotic matter in quantum fields. Do the laws of physics truly forbid negative energy in useful quantities, or is it possible under extreme conditions? Finally, wormholes make us confront cosmic censorship, the idea that singularity should always be hidden behind horizons. If wormholes are traversable, they may expose the bare bones of spacetime in ways Einstein never envisioned. Through such thought experiments, wormholes become laboratories of the mind, allowing physicists to probe the very boundaries of physics. But wormholes don't just capture the imagination of scientists. They have also played a significant role in science fiction. Wormholes are often depicted as portals or gateways to other parts of the universe or other times. This is because wormholes, if they exist, connect to points in spacetime. This means that if you were to travel through a wormhole, you could emerge far away, or even in the past or future. In cinema, wormholes are often portrayed as visual spectacles. Films like Interstellar use computer-generated imagery to depict wormholes as awe-inspiring and mysterious objects. But wormholes aren't just visually arresting, they also serve a narrative purpose. In many stories, wormholes represent the unknown and the possibility of new discoveries or adventures. They can also be used to explore themes of time travel, alternate universes, and the nature of reality. Wormholes have appeared in numerous films, TV shows, and books over the years. Some famous examples include the Gateway to the Stars in Star Trek, the Stargate in the Stargate franchise, and the black hole that becomes a wormhole in Event Horizon. One of the reasons wormholes resonate so much in popular culture is that they embody two human longings: the desire to explore and the desire to transcend. The exploration, crossing vast gulfs of space in an instant, transcending time, defying the arrow of time, and perhaps visiting the past or future. Wormholes offer a tantalizing glimpse into the what-ifs of the universe, capturing our imagination and inspiring countless stories and theories. Ultimately, wormholes remind us that science and imagination are not opposites, they're partners. Theoretical physics asks, what if the universe works this way? Science fiction asks, what would it mean for us if it did? Together, they ensure wormholes will remain a topic of fascination for as long as humans look to the stars. So what do you think? Are wormholes just a fantasy? Or do they really exist somewhere in the vastness of space-time? Let me know your thoughts. There's a new world right outside our own, a universe brimming with possibilities accessible only through tears in the fabric of reality. Welcome to my channel. Today we're rediving into a topic so mind-boggling, it challenges the very essence of space and time itself. Brace for impact, because today we're talking wormholes, those enigmatic cosmic tunnels that could be the key to humanity's future or lead us down a path of eternal fascination without any practical use. So grab your thinking caps, dear viewers, because we're about to embark on a journey through the theoretical landscape of wormholes. Are they the highways to the future, or forever out of reach? Our story begins at the very edges of possibility. Imagine for a moment if space and time were not a rigid, unyielding grid, but instead a fluid canvas where points could be connected by unseen threads, allowing us to traverse the universe in ways previously thought impossible. This isn't science fiction, but theoretical physics. Wormholes, also known as Einstein-Rosen bridges, are hypothetical structures that connect to distant points in spacetime. But here's the kicker: they might just be the key to unlocking a future beyond our wildest dreams. Picture a vast cosmic highway system where galaxies are merely a hop, skip, and a jump away. Sounds pretty wild, right? Well, let's delve deeper. One of the most exciting implications of wormholes is the prospect of instantaneous travel across interstellar distances. Imagine hopping on a spaceship and arriving at a distant star system within mere seconds. With wormholes as our cosmic guide, this fantastical idea ceases to be science fiction and morphs into a legitimate possibility. No more waiting eons for spaceships to crawl across the void of space. Wormholes could revolutionize space travel, shrinking the universe and making once distant worlds our next-door neighbors. But wait, there's more. Wormholes might even hold the secret to time travel. Yes, you heard that correctly. These cosmic oddities could allow us to journey not just through space, but across the very timeline of existence. Picture stepping into a wormhole and emerging in the past, or even the future. Suddenly, H.G. Wells's fictional time machine becomes a theoretical possibility grounded in the laws of physics. But before you start planning your time-traveling adventures, remember, we're still in the realm of theoretical physics. Wormholes remain elusive, existing only in mathematical equations and computer simulations. We haven't detected one in the vast expanse of our universe. And even if we did, The engineering challenges of harnessing them would be nothing short of Herculean. Traversable wormholes, meaning ones that don't collapse before you can get through them, would require exotic matter with negative energy densities. We have yet to discover such matter in our own universe. It's possible it might exist, but it's equally likely that the mathematics describing wormholes is correct, but they themselves are merely illusions. Nevertheless, the allure of wormholes goes beyond their practical applications. They force us to confront the very nature of space and time. By studying wormholes, even the hypothetical ones, we gain a deeper understanding of our universe and its underlying laws. They challenge our intuition and push the boundaries of what we believe is possible. The concept of wormholes was first proposed by Albert Einstein and Nathan Rosen in 1935. They were trying to find a solution to Einstein's equations of general relativity, which describe how space-time is warped by mass and energy. What they came up with was a theoretical passage connecting to distant points in space-time, a tunnel through the fourth dimension of time. Since then, wormholes have captured the imagination of scientists, science fiction writers, and space enthusiasts alike. Now, let's talk about the science. The scientific study of wormholes is rooted in Einstein's general theory of relativity, which posits that gravity is a result of the curvature of space-time caused by mass and energy. According to this theory, massive objects warp the fabric of space-time around them, creating dips and valleys much like a bowling ball on a trampoline. Now imagine taking this warping of space-time to the extreme. Picture two distant points in space-time being pulled together until they touch. Keep pushing, and the points collapse, forming a tunnel-like structure. That's essentially how a wormhole is born. But here's where things get really interesting. A wormhole is not just a tunnel through space, it's a tunnel through space-time. This means that if you were to travel through a wormhole, you wouldn't just arrive at a different location in space, you could potentially end up in a different time as well, enter the realm of time travel. But wait, time travel raises a host of paradoxes. If you travel back in time and change something significant, wouldn't that alter the very existence of the wormhole itself? It's a mind-bending concept that challenges our understanding of cause and effect. Here's where things take a turn, toward the bizarre. The mathematics of wormholes suggest that they are as real as the space in which they tunnel. This means that if you were to explore the interior of a wormhole, you would encounter a strange and unfamiliar reality. The rules of physics as we know them might not apply. Time could flow in reverse, but you might even encounter alternate versions of yourself. It's a world of endless possibilities, but one that's likely to leave you disoriented and confused. So let's talk about the engineering challenges. We've established that wormholes are theoretically possible, but the practical hurdles of creating and harnessing one are monumental. To create a traversable wormhole would require exotic matter with negative energy densities. This is a form of matter that has yet to be discovered. Additionally, stabilizing a wormhole would be a Herculean task. They are inherently unstable structures prone to collapse. And even if you manage to stabilize one, navigating it could be perilous. The immense tidal forces near a wormhole could stretch and tear apart anything that ventures too close. In short, creating a functional wormhole would push the boundaries of our current technological capabilities. It would require advancements in fields such as particle physics, gravitational physics, and engineering that are currently beyond our grasp. So, while the idea of wormholes is fascinating, we must remain grounded in reality. There's a reason why wormholes are relegated to the realm of science fiction. They challenge the very fabric of our understanding of the universe. And until we unravel the deepest mysteries of space-time, they will remain just beyond our reach. The hunt for wormholes continues. Astronomers are constantly scanning the skies for signs of these elusive phenomena. With new telescopes and gravitational wave detectors coming online, we are becoming more sensitive to the subtle signals that wormholes might emit. While we haven't found any conclusive evidence of wormholes yet, the search itself is expanding our knowledge of the universe. Who knows what other wonders we might uncover in our quest to find these cosmic shortcuts? The future of wormhole physics lies in the hands of scientists pushing the boundaries of theoretical and experimental physics. As our understanding of the universe deepens, so does our ability to explore the realms of possibility. Who knows what the future holds? Maybe one day we'll stumble upon a wormhole and our perception of reality will shift forever. Our story isn't over yet. The tale of wormholes is a testament to the boundless curiosity of the human spirit. Whether wormholes turn out to be a scientific curiosity or a gateway to the stars, the pursuit of knowledge is a journey without end. So keep looking up, dear viewers, and never stop asking questions. The universe might just surprise you. If you enjoyed this journey through the wormhole, make sure to give this video a thumbs up and subscribe to my channel for more thrilling explorations of the cosmos. Till next time, keep pondering the mysteries of the universe. And remember, in the grand tapestry of existence, we are all connected by an invisible thread of curiosity and wonder. Thank you for joining me on this adventure. Till next time, keep looking up and never stop questioning the extraordinary.